Hello, good afternoon, everybody. Thanks for coming again to this series of seminars of Quantum Spain Talent Q. We're very glad to have today with us Juan José García-Ripoll. So Juan José is probably known, if not to all of you, to many of you. He's a long-range interacting, I would say, boson. Yeah, long range because he has links to so many people and touches upon so many different aspects and levels of this quantum world. And a boson because you can always come close to him and you will feel no repulsion at all. So on the academic side, he studied and doctorated in Madrid, in the Universidad Complutense. The Universidad Complutense, Juanjo. I don't know if to ask for a 1 minute silence uh, for the universities in Madrid. He spent then 5 years postdoc at the Max Planck Institute for Quantum Optics in Munich. Yeah, his research is very miscellaneous, ranging from the very fundamentals to concrete devices and quantum algorithms. Juanjo is also a policymaker. It's fair to say that in the shaping of the quantum community in Spain, Juanjo is one of the leading voices. A large number of centers, researchers, students have benefited from his energetic initiative. I was going to say that Juanjo is an influential person and in this realm. Now, honestly said, I wish he was much more influential. So today he's going to give us his insight in one of the many topics he touches upon, namely distributed quantum computing. The concrete title is Superconducting Quantum Networks for Quantum Computers. Juanjo, thanks for your valuable and scarce time. So at the stage is open for you. So everybody, if somebody wants to ask questions, we will unmute him. Just raise the hand. But if not, you can defer the questions either for the end or write them in the chat. So Juanjo, the floor is yours. Thanks.
Thank you, Javier. I hope you can all hear me well. Thanks again for the invitation to participate in this seminar series. It's a pleasure to collaborate with all this outreach work that you have been doing for a very long time. I hope it continues in the future. And also, thanks a lot for the welcoming introduction. It's very generous of you. And well, I feel a little bit embarrassed. I chose a topic that's a little bit exotic because I wanted to look a little bit into the outlook of what we are doing in quantum computing and quantum simulation. So it's 100 years of quantum science that we are celebrating this year, the International Year of Quantum. But it's also more than 40 years of quantum computing and quantum simulation. If you go back to the Feynman lectures on quantum computing, on computing, and his talks in these seminars in MIT about how to build simulators for quantum theories, or you think about Paul Benioff's works or David Deutsch's works, we have been running for many years a program that started in a very conceptual way, very foundational way, a little bit fringe science, and is now becoming a reality with first machines that we are building that hint at the possibility of scaling up. And it's a revolution. We can now control matter at the quantum level, both with neutral particles, for instance, or with charged particles here, the trapped ions, where we can control the quantum states of nature with extreme accuracy. It's natural that we can do these things with atoms, where we can explore phenomenology such as, for instance, trapping the individual atoms, but also manipulating their electronic speed states in the case of ions, or even witnessing phenomena such as quantum tunneling with these particles. And probably it's not a surprise that we can do this because atoms, they are very small. They are particles that live in a quantum realm for which, according to quantum mechanics, the energy barriers are not necessarily unsurmountable, and wave functions can tunnel through them with certain probabilities that could be measured in the lab. This is a nice spin-off to discuss something that, I could not give a talk without mentioning this year's Nobel Prize in Physics, because it was awarded for seminar experiments that are in the foundations of what I'm going to talk about today. So this was awarded to John Clark, Michel de Boret, and John Martinez for the discovery of microscopic quantum tunneling in electrical circuits. It's something amazing is the facility, the possibility to explore quantum mechanics, not with isolated particles in vacuum, few electrons, few protons, very small systems, but with real circuits, where you can start building, for instance, a cable, a superconducting cable, and put a little bit of isolated material in between these two superconducting leads and explore the transport of current through that cable. And what they observed is that in certain configurations, you could have stationary states of the system, and if you apply a current, the classical potential that this describes the energy of this circuit tilts down, and there appear bound states that can tunnel into a continuum. And these bound states are defined in terms of variables which are called fluxes. And in these Hamiltonians, you can predict the tunneling of these excitations into a continuum where you can measure them by the emergence of a voltage state. This is something very singular because what we are talking about here is having a circuit with some macroscopic variables like charge difference between these two leads and the flux or phase difference between these two bonds in the Josephson junction, and exploring quantum effects and the quantization of the energy and the tunneling of quantum states from localized states to delocalized states, where those states involve all the particles that are moving through the cable, or a significant fraction of them. So this is quite something. And from here you can guess that there emerges the notion of a qubit as a two-level system that can be metastable under certain conditions, where we can raise these barriers and make them isolated and quite well trapped. Indeed, this is the case. So the experiments of quantum tunneling were the beginning, but very short thereafter, people like John Martinez used these kind of devices to define artificial atoms where they could trap the circuit in two macroscopic states that could be manipulated using microwaves. We have gone a long way from there. These are not the best qubits that we can build. There are better qubits nowadays, like the Transmon. These are these superconducting islands with a small Josephson junction at the end that allows tunneling of particles in and out of the island, and which are much more stable. They behave more gently. They are better against behave better against fluctuations of a charged environment. They cohere more slowly, and they are the foundation for all quantum computing designs in all major labs, and also in all major companies like IBM Q, IBM Quantum, or Google Quantum AI. And so we have moved from those experiments in the 80s with microscopic tunneling of currents towards architectures that now involve more and more qubits, hundreds, even thousands of qubits on a single chip. And this is posing now engineering challenges. And you can already guess it here. So you can guess that when we put a chip here, a superconducting chip is much bigger than a typical semiconducting chip. So you need bigger fridges. And this is a picture of a fridge in IBM, which they had to make bigger to fit the new devices. Google also has fridges that are 4 or 6 times larger than usual fridges. But also it's a challenge from the point of view of control, because these qubits have to be manipulated. They need a very artisanal control. Each qubit needs separate controls. And you need a lot of cables to control a lot of qubits. And at some point, this becomes more than an engineering challenge, a roadblock, something that we have to avoid. And there are different ways to do that. Some are more based on engineering, as I said, packing these cables into different kinds of cables which are more densely fabricated, or moving the control electronics to inside the fridge, what is called cryogenic electronics, where it's closer and there are less cables to communicate with the chip. But there are other approaches which is simply architectural. It's to change the way we do things. And one approach that was was posed a long time ago is to go in the route of dividing the experiment into more manageable components. This is what is called distributed quantum computing. The idea is that each of these experiments is quite heavy, and it can be packed together with its own electronics. And if it doesn't fit all in the same fridge, we can have different fridges talking to each other and exchanging information or cooperatively computing in the same task. And this is a way to scale up a device. Arguably, this will happen even if we don't have scaling needs, because if you look at the way computers are architectures, they are really lots of different processors talking to each other. Nowadays, all those processors tend to be fabricated in the same chip because it makes things faster and more efficient, but we have many things that have to talk to each other. So moving along this vision also is a way of progressing the state of the art of quantum technologies towards a world of connected quantum devices. Amazing thing is the fact that this idea was posed very early on. Remember that the first proposal to do a real physical quantum computer with trapped ions, 1995, by Ignacio Cirac and Peter Soller, was very shortly after followed by this paper, 1997, where they were exploring already how to connect qubits living in different experiments. So they already thought about the need of transporting quantum information between different devices, and in parallel or shortly after this paper, there was a mathematical paper laying the foundations for distributed quantum computing. This idea is very natural. What we aim to do is to transfer information from qubits that are stable, but like this transmons. Shortly after this paper, there was a mathematical paper laying the foundations for distributed quantum computing. This idea is very natural. What we aim to do is to transfer information from qubits that are stable, but like these transmons that are in a chip that cannot be moved around. But we have as a tool the photon. A photon is a quantum object that is can stay coherent for a very long time, can move long distances. So we can think about transforming the information that is stored in this atom, a real or an artificial atom, into a traveling photon that carries that information. And that is how they thought about it. So for instance, they thought about, in their case, of atomic systems with two degenerate ground states, and through a clever combination of laser fields, they would map the information of a qubit being in the E or G state to having a photon or no photon traveling through the waveguide. This photon or no photon is reabsorbed, and the information is mapped from one cavity to another. This is a very much quantum optics paradigm about atoms that generate photons or absorb photons, but it was very difficult. So the idea is from 1997. It took a lot of time, 15 years, to be produced for the first time deterministically in the lab of Gerhard Rempe using atoms trapped in a cavity. And you can guess that where the challenge is coming from. Indeed, first you have to convince to bring an atom inside the cavity. Then you have to make a cavity that can absorb almost all the light that the atom produces, and match this to a receiving node, control the emission of a photon, and so on. It's quite difficult, but it was a proof of concept experiment that lays the foundation for what I'm going to discuss today. There are other platforms where this idea is being looked at. The case of neutral atoms is quite difficult because, this single atom is not very useful. But if you have already a quantum computer made of trapped ions and you can put a microscopic cavity nearby, you can generate photons selectively from these atoms, as demonstrated in Innsbruck by the group of Ben Lanyon. So in principle, this is something that in atomic physics is gaining traction again as a tool for distributed quantum computing, but also for quantum communication and entanglement. In our case, we got involved in this topic shortly before the pandemics. What happened was that the group of Andreas Wallraff had created this station with two fridges connected by a microwave tube, and that was like a prototype of two connected quantum processors. We, together with Peter Ravel as coordinator, Andreas Wallraff, Johannes Fink, and people from Max Planck Institute, Ignacio Cirac, and Jordi Tura, we applied for a project to scale this up. To scale, not mean having more fridges, but at least make it larger and explore really a network where things propagate across these waveguides. And that was the starting of a very nice, a lot of fun of research together with all these people. I'm going to talk about the theory part, which is where we were more deeply involved, and where we applied our understanding of quantum optics to model and design improvements around these devices. The picture on the left describes an electronics vision or schematics of what the device looks like, but essentially it's like a qubit connected to a chain of resonators, microwave filters, that allow the qubits to either be isolated from this cable or to become in resonance and then inject energy into the waveguide. The waveguide transports the information between different nodes, which are more or less symmetric, although in fabrication you can never produce, in this case, identical qubits, but we can assume that theoretically at the beginning. And so we can map this as we can map the qubit and the resonators as qubits, two-level systems, living inside photonic cavities and connected through some decay rate to the cable. This is a collection of photonic modes that transports the information to another cavity where the qubit lives and where this qubit can extract the energy. And this is, as I said, it's a model that contains only things that we know from quantum optics, propagating photons, photons confined in cavities, and light-matter interactions between the qubits and the cavities. What these experiments bring to the picture is that something that is somehow difficult to do with atoms is more easily done with circuits, is the control of interactions between the qubit and the cavity. This can be done with many different ways, but essentially there is a microwave that controls the transfer of energy between the two-level system and the photonic degrees of freedom, and allows us to both change the amplitude and the phase of this complex number. So the research program that we started essentially aimed to demonstrate that distributed quantum computing was possible in this platform. If you think about what we need, there is a very simple list, a shopping list. The first thing we need to do is we need to be able to transduce the information from the stationary atom to a propagating photon. The next thing that we need is to shape these photons so that they can be, in a later stage, reabsorbed at the receiving node. And once we have this, we have to show how this primitive, which maps a qubit from one place to another, is essentially like a primitive that swaps information on a quantum chip, can be used to create entanglement or create distributed quantum operations. And for us, the most important part was the last one, where we really needed to optimize the design and show that this can be competitive with computation inside a single chip. But let's discuss the physics of the first part, which is very nice, because it's already quite exciting. It's the idea of taking a two-level system, which can be in a 0 or a 1 state, and map it into a superposition of having or not having a propagating photon. And the theory that we developed basically assumes a chain of cavities or filters, microwave filters, and we are solving an inverse problem where we know the shape of the photon we want to create, and we have to find out the design of the time-dependent light-matter interaction that we need to control between the qubit and the cavity. If you think about this from the point of view of a wave function, you have a very simple wave function where you can have an excitation living in the qubit, an excitation living in the cavity, or the excitation living in these photonic modes in the waveguides. And we can trace out these degrees of freedom and end up with an equation that only contains the two-level system and the cavity. And we can essentially find out what is the shape of the control as a function of the shape of the photon we want to create. And this is important because, as I said, we need to control this shape. If we simply let this coupling on, this produces a wave packet with an exponential profile. It's like a very sharp wavefront that the atom cannot absorb. Traditionally, it has been said that these photons need to have time reversal symmetry so that the process of emission is equivalent to the process of absorption. This is not necessarily true. We can have different shapes, but what is needed is that we need to have a particular shape with a certain speed of growth and decay of these tails, because if you fall outside that limit, there will be no mathematical solution to this equation here. If you think about it from the point of view of quantum mechanics, this is very similar to the experiment of the Nobel Prize this year. What we are doing is tunneling the information that is here confined in this circuit. There is a excitation of charge or excitation of current, depends on your qubit, and allowing it to transform into a photon that leaks out into a continuum which is this cable. And we are doing this in an experiment that measures meters, has meters of size, tens of meters of size, and weighs a ton or 2 tons with thousands or tens of thousands of screws. So it's really exploring quantum tunneling, quantum superpositions in a macroscopic environment. This idea can be generalized to different setups. The actual experiment looks more like this. There are 2 filters that protect more strongly the qubit from the decoherence induced by relaxation into the waveguide. But the theory is just the same, and you can simply solve a little bit more complex equations. The nice thing is that if we do proper wave packet shaping, the control that we have here, we can reverse it in time on the other side of the link, the quantum link, and use it here to reabsorb the photon. So essentially, we have designed a control to produce a photon. This would be the time-dependent light-matter coupling between the qubit and the cavity, and we apply the time reverse control on the other side. And what you see is that if you do a very good design of these controls, initially your qubit is excited. This is the probability of qubit 1 being excited here on the left. If the qubit is excited, it relaxes, putting energy into the cavity, which quickly goes into the waveguide. And the energy that is in the waveguide eventually reaches the cavity, and after a certain time, it is reabsorbed by this control into the second qubit. The motion from here to here, it achieves almost perfect fidelity, and is a mapping of the excited state of the qubit on the left to an excited state of the qubit on the right. Vacuum states will produce no photons, so nothing is changed. So that means that if you have here a superposition of 0 and 1, it can be mapped of the proposition of having a photon or not photon, and then once the photon is reabsorbed, is mapped into a superposition in the second qubit. So it's what is called a state transfer. If you do things right, the phases are preserved and they are matched. The nice thing about these designs is that we can customize them very easily. We can, for instance, compensate for the fact that cavities may not be identical. They don't need to have neither the exact frequency, or for instance, they don't need to have the exact same coupling strength to the cable, because there can be small imperfections. And nevertheless, by mathematical processes, we can adapt the controls to achieve still state transfer. But there is one limit in which we can do this, which is very extreme. Because you think about what they showed you before, the equations that we solve, they only involve the qubit and the cavity. We have traced out the photons. Why? Because mathematically, we are solving the equations in a limit in which the photon is moving away from the cavity and is never going to influence back the process of emission. So we have forgotten about the photons. And this is only rigorously feasible if the cable is very long. But it turns out that we can crank up the shape of the controls to make these controls slower and slower and slower, to a point where the emission of the photon from the left node is happening at the same time as the photon is being received on the other side. This is a very strange limit in which the actual length of the photon exceeds the length of the cable that we have in the experiment, would be this length here. It's a strange limit because in that limit, it's a limit of a short cable. You can see the modes of the waveguide as very well separated in frequency. There is not a continuum of modes, and the approximations that we are using typically in quantum optics, they should not apply. But still, they work. Okay, they work so well that actually that's the best regime. If you look at the infidelity of a state transfer in the Zurich experiment as modeled by our equations, you find that when the photon is very short, here, where the bandwidth of the cavity is very narrow, you can have extremely small infidelities, 10 to the minus 7, 10 to the minus 9. This is the error of transmitting a qubit from the left node to the right node. What we found surprising is that if we increase the length of the cable, or we shorten the length of the photons, we found this deterioration of the fidelity. So the errors grow exponentially. There is an explanation for that. The waveguide that they have in Zurich is actually a tube. And a tube has a certain transverse section, with a gap of frequency. So the dispersion relation of the microwaves in the tube is not perfectly linear. There is some curvature, and there is some distortion that when you make the photons shorter, means that they explore more frequencies, they increase the bandwidth, and they can see the curvature and they get distorted. If we stick to this limit, what we have found is a way to find out the fastest state transfer protocols in that regime. Previously, people had studied this problem, assuming that the qubit talks to a single frequency mode of the cable, and then the other qubit does the same, and they both exchange information as if the cable was a single cavity. That gives rise to certain protocols based on stirrup, adiabatic transfer, and so on, which are way slower than the protocols that we have designed with this approximation. So in this sense, they are close to optimal with extremely good infidelities, very low infidelities. If we go to the limit, as I said, the problem is that the photon bandwidth, because the photon is very short, becomes very broad in frequency, and it can see the curvature of the dispersion relation. A simulation that's very easy to do is to let the photon bounce back and forth inside the microwave, and what you see is this. Basically, the photon gets broader and broader and broader, and is being distorted. Is this a limitation? Well, maybe not. The problem is that we have engineered this coupling to produce a certain shape of a photon. And we have engineered this coupling to absorb that same shape. What we see from the experiment is that the shape at the receiving point is not the one that we had predicted. So there are two ways to fix this. One way is to apply what is called a predistortion here, is to create a wave packet that when it arrives here, it self-corrects. Or the other possibility is to understand that what is the wave packet that is arriving at this side of the link and introduce the corrections in the receiving control. We can do both. In practice, for very long links, you need to do both. And what you find is that indeed you get orders of magnitude improvements, and the exponential slope that we saw before is corrected down to a level where it is competitive with operations that happen inside the same chip. So we are below 10 to the minus 4 errors in the waveguide. There is something very funny happening here, because you could think, okay, let me correct higher orders of the curvature. Well, what happens is that when you are implementing these corrections, you have to do some chirping of the light matter interactions, and you're basically pushing the limits of the theory as we know, we usually do in quantum optics. This will be the equations we derive with typical Markovian models. To go even further, you need to develop non-Markovian theories that describe the time-dependent controls that we're doing here. So essentially, we are changing the light matter interactions in a time scale at a speed that is comparable to the photons themselves. So this more or less sets a limit of what we can do analytically, and we need to find other tools like quantum control to go further. But as I said, by correcting things, we can go to errors that are very, very low and which are similar to the error of moving a qubit inside a single IBM chip or other devices. I think there was a question, and I don't know, is me wrong? Heard a beep? No, I'm wrong. Okay, so because the infidelity is so low, then you can treat this as a one more primitive. So I forget that I have two quantum processors, and I introduce a new primitive in my pseudo Qiskit that moves qubits from one qubit to another. And this way I can have a qubit here, I move it to the other processor, I do an entangling gate, and I bring it back. And the outcome, it is as if we had made a distributed quantum gate. It's a very simple protocol, nothing new to do there. The question is, how scalable is this? Because, I mean, I have shown that I can do a one-ton experiment to move one qubit. But that's not very promising, no? Because if I have to do one link, one qubit for each qubit I have to send, that's really not scalable. What we would like to be able to do is to have the possibility of sending multiple qubits. Either the same qubit can send multiple photons, or more qubits can be connected to the same cable and send photons simultaneously. There are different approaches to do this task, which is called multiplexing. A trivial approach would be to use a time-being encoding where photons are sent one after another. So you could have one qubit that acts as buffer, where other qubits are pushing the information, and they are being routed to the other side of the link, one after another. That can be done, but it's not very efficient because the more qubits we have, the more time we need, and the more coherence our experiment we have. There are other possibilities. One of them is to use different orthogonal modes within the same waveguide. This is called mode encoding. It's a little bit more complicated. I will not talk about it. But there are experiments happening in Nakamura's group and in Zurich as well on this line of work. And the topic I'm going to talk is very easy, is frequency encoding. We are going to create wave packets with slightly different colors. Why is this useful? Well, as I said, it's one very important task is to optimize the channel capacity. We cannot have many cables. We want to send the most information through the same cable. It's a little bit like what we do with USBs. No, we try to send the most bits for the same channel as possible. The other interesting approach is that if we can send more than one qubit, we can also send entangled states. And that's a resource by itself, but it's in particular a very important resource to do error correction, because our cables, even if they have very little errors, they still will have errors. So it would be interesting to research a transfer of information that sends data in a correctable way, where errors can be detected and can be fixed. And for that, we need multiple qubits that are correlated with each other according to the protocol that we define. And, well, there is a very trivial, if you know a little bit of quantum optics, the frequency multiplexing is a little bit trivial, because what happens is that we have two quantum objects injecting energy in photons that are in two wave packets. And the ejection is never a problem. The problem is when they arrive to the right. These two cavities need to distinguish those two wave packets. So the errors associated to this multiplexing are going to depend on how distinguishable those wave packets are. So essentially, one measure of potential error would be the overlap between those wave functions, and the overlap is best measured in frequency space. So if your two wave packets have certain bandwidth and they are centered into different frequencies, you can compute their overlap. And for typical wave packets, well, this overlap may decay exponentially with the frequency difference. Indeed, this is the case for the wave packets I was showing you before. This will be the theoretical predictions. This is the overlap of the photon wave packets we were engineering. This will be the overlap, the errors in the state transfer. Two qubits sending two photons simultaneously, centered in slightly different frequencies. And as you see, as the frequencies move apart from each other, the errors and the overlap both decay exponentially, and we achieve the baseline. This will be the errors for sending the two qubits one after another independently. So it's just a matter of optimizing your resource, which is the frequency space, the bandwidth that we have available, and moving the photons away from each other in frequency space as much as we can. This is not such a huge number. See here that moving it 5 times the natural bandwidth of the photons, when kappa is around 20 megahertz, perhaps, is not a lot of space. And that means that we can have many emitters sending simultaneously photons at very decent rates. So this would be the ideal situation would be when the separation between photons is between 5 times the bandwidth or 6 times the bandwidth of the photons. And you see that numbers here, 10 to the minus 4, are achievable for 10 qubits or up to 100 qubits. So it's decent. We have been doing these estimates in the last years, and we are confident that even for relatively long waveguides, 30 meters, we could send up to 10 qubits accurately, simultaneously in the cable and connect both processors. And those are the theory estimations, of course. This is more like a long-term perspective of what can be done. And I was running quite fast through it, but let's recap a little bit, but now changing the point of view. And instead of looking at the theory, let's look at the experiments, what can be done right now. And the state of experiments, as I told you, is that these things have been revisited in the last 7 to 8 years, because as I said, the proposal by Dirac, Thor, Mabuchi, and Kimber is quite difficult to achieve with atoms. And only recently we have high quality superconducting devices where we can explore this with a sufficiently strong light-matter interaction, which is what is the main ingredient of these state transfer protocols. One of the first experiments in study these ideas were done in the same chip. This is an experiment by Andrew Cleland and Dave Schuster. And what you see here is a superconducting qubit on one side, another superconducting qubit on another side, and they are both coupled to this meandering waveguide. So it's basically a 78 centimeter cable printed on the same chip. The nice thing about this experiment is that they can control the qubit cable interaction using the same tool that Cleland and Martinez developed in Santa Barbara when they were exploring quantum computing. And they can indeed see that both qubits, when they are coupled to the waveguide, they are indeed interacting. And if they are switched on, they can experience basically Rabi oscillations. They can exchange energy between each other, and this can be measured experimentally. But with 78 centimeter transmission line, you can already begin to explore the wave packet shaping that I mentioned before. So they can basically control the time dependence of these couplings here, not just to activate them and leave them on and see how the qubit exchange energy at very long times, but really to shape the emission of a photon from one qubit and see how this photon can be reabsorbed multiple times. When there is no control, the reabsorption is imperfect, but as soon as you do the wave packet engineering that we mentioned before, you can get almost 100% reabsorption probability of those photons. This is an experiment that happens in the same chip, but all the ingredients of what I mentioned before are available there. The challenge is now to bring it to a macroscopic scale to really connect different processors. And this is the outcome of a Superconducting project that I mentioned before. It's the experiment that was in Zurich. It's a 5-meter connection between two dilution refrigerators, has been upgraded to a 30-meter connection with 5 tubes, 5 concentric tubes, the inner tube being at temperatures that goes between 10 millikelvin and 20 millikelvin at the middle point. This is a reinforcement fridge that helps cool the whole setup in the middle of the connection, and there is a very nice video in the Andreas Wallraff YouTube channel and the group channel, where they both provided a video of this long experiment in the basement of ETH Zurich, as well as a popular description of the experiment that they were able to achieve. Because what did they do with this? What happens is that if you do an experiment that is 30 meters long, then photons take 100 nanoseconds to go from one station to another. Why? Because basically those tubes are empty and the photons move at the speed of light, so there is a limitation, a causal limitation of how fast information can travel from one quantum processor to the other. And this allows you to do very funny things in quantum mechanics. If your information takes some time to arrive, you can prepare a quantum state between those two processors, entangled states, and do measurements in each quantum processor, which are faster than the time for classical information to propagate from one node to another. In other ways, you can do Bell test experiments where the measurements happen so fast that there cannot be any transfer of information at the speed of light that explains the correlations in those measurements. Of course, there could be superluminal theories that could explain those experiments, but we don't really believe in them. But this is a setup where that kind of foundational experiments can be explored. It's a very weird way to do that. It's a two-tone experiment, but we can both explore transfer of quantum information as well as very foundational experiments in quantum mechanics. And this is what they did. They showed that they can create a superposition of qubit being in 0 and 1, it's a qubit, an excited qubit, sorry, and transfer with a 50% probability amplitude half of the probability of that qubit into a propagating photon that is reabsorbed at the right. So what you end up is with a state where you have a superposition between this qubit being excited and this one in the ground state, and the opposite situation. This one is excited and this one is in the ground state. This is at the beginning of the experiment. Then they do basis rotations based on the best state protocol, best state testing protocols, and they can do that in a very fast way to get the outcomes that are then correlated classically to see whether any inequality is violated. And indeed, they saw some small violation of inequalities. This experiment is still like a proof of concept. The fidelity of state transfer is limited, it's close to 80%, but it's a very exciting demonstration of these ideas. Since that experiment, there have been other works in the literature doing similar things, but inside the same fridge. For instance, there was a very nice preprint from a group in China connecting two superconducting processors with a 64-meter coaxial cable to another superconducting processor, all wound up inside the same fridge. This doesn't test non-locality. It simply tests that you can do very high fidelity, 94% fidelity, I think, state transfer between these two devices with more or less conventional coaxial cable. But they also explore doing these things at shorter distances with small quantum processors that talk to each other, again, through shorter coaxial cables, where they can implement this kind of networking protocols. So this is extremely exciting because we are, on the one hand, achieving the paradigm of distributed quantum computation and also connected quantum devices, and we are understanding how quantum optics allows us to design these quantum information channels. But on the other hand, we are doing all these things thanks to the superconducting circuits at a macroscopic scale. And we are moving towards a new territory. One thing that we looked at in one of the first works we did devoted to the study of these links was to see if we could do this in a more passive way. Because what I showed you before required control at the emitting and the receiving nodes. And we thought, okay, let me try to do an experiment where this qubit is in a stationary state. I don't change this interaction with the cavities. And it's only this one that is going to create a photon that is sent and reabsorbed. There were many experiments, as well as theoretical studies, of how a photon that is reflected by a cavity or a resonator can acquire a different phase depending on the state, the quantum state of a qubit that is inside that cavity. This is a passive gate. So essentially, a photon that arrives to the cavity is reflected with one sign or the opposite sign, depending on whether the qubit is in the 0 or in the 1 state. And this is true for photons, superposition states, and other configurations. So this is basically a quantum gate between a traveling photon and a localized qubit. And you can use those gates to achieve entanglement between qubits, because what we know now is that we can generate a photon, send it to the other station, and reabsorb it using a well-engineered control. So it's basically a protocol where we have two qubits in arbitrary states, and the state of one qubit is mapped into a propagating photon if this is excited, and then the photon collides with the other qubits in its cavity and acquires or not a phase, and it's later on reabsorbed. So you achieve a control phase gate. And it works, more or less. So basically you have to study the scattering matrix of the photon with the two possible states of the cavity, depending on the qubit state. One qubit state shifts the cavity frequencies to one side. The other qubit state shifts the cavity resonance to the other side. And when this difference is large enough, you achieve a difference of pi in the photon state, which is sufficient to make this gate. And it works. So with a relatively good qubits, you can get a gate with certain fidelity. But for us, what this revealed is that we could create long-distance interactions between remote quantum objects where those interactions take some time to happen. So you can think it like you could have two electrons, and the electrons sense each other's state by a dipolar interaction. But those dipolar interactions, typically we think about them as instantaneous things. They don't take a lot of time to propagate. We simply think about an atom, another atom, and they have dipolar interactions, and we compute the collective eigenstates as something that's stationary with a time-independent Hamiltonian. But here we have something different. We have the possibility of quantum objects to interact with each other with retardation. And that's the natural thing, the natural way in which quantum networks are going to be built. So we came up with the conclusion that this research on quantum networks opens a new research field, where we have quantum particles, which are the nodes of a network, that are interacting with each other through the propagation of delayed photons, where the delay of the photon becomes a physically relevant parameter of the whole network. And it's very different from traditional models of many-body physics, where we have instantaneous interactions, even if they are non-local. Now, the timescales of those photons to propagate will compete with the intrinsic timescales of the quantum particles themselves, and it creates a very nice landscape of many-body interactions in a quantum network that is macroscopic, happens at very large distances, where we can explore the correlation of these particles in very extraordinary regimes. And we have started to look at how this works. It's not easy to develop a theory for a system of particles that interact with each other with retardations. We have first hints that we can build operator equations, which are more easy to handle than the Schrödinger equations, where the dynamics of one quantum emitter, like a two-level system, is influenced by the state of the waveguides, initially probably in the vacuum state, and the stream of photons that is produced by other emitters in different points in the past. We can do approximations some technical approximations in these equations, and we end up with highly correlated models of interacting two-level systems with delay differential equations. Do they work? Don't they work? Actually, they seem to work. They seem to describe the dynamics of the quantum link. For instance, we put the experiments I showed you before of a quantum link with two nodes exchanging photons, and the models accurately predict the dynamics of how those qubits interact photons, in this case, in the regime in which we don't do wave packet shaping. But we can now explore networks, bigger networks, where we have atoms that can be excited, and where you can see phenomena such as subradiance. Like, for instance, you can have two atoms that are initially excited, two quantum nodes, are separated a certain distance, and after the photons that are emitted by one atom arrive at the other node, the correlated state is established, and the system doesn't evolve, and you have distributed entanglement between those particles, or regimes where the opposite happens. Indeed, it's a very curious platform where we can study collective phenomena. In this case, it's a 1D network, which is what we started to look at, and you see phenomena like the emergence of light cones. So this would be the intensity of the light emitted by an array of quantum nodes with a certain separation. And you see that as time passes by, when the photons emitted by one atom reach the neighbor, the emission of light intensifies. And every time we see one photon arriving to a further away node, the emission speeds up. And after some time, we find out what is called a super radiant peak, a collective burst of energy that hints at some kind of collective enhancement, correlated dynamics of the network. In this case, it's a 1D network, but what we can do right now, but it can be explored in this regime. And we find that this is very nice, that the fact that when the photons emitted by the first qubit or first node reach at the end of the waveguide, we achieve a maximum correlation, and the whole system begins to see each other, despite the existence of these light cones, and the dynamics is fully correlated at this point. This allows us to distinguish qubits, which are nonlinear objects, from cavities that don't exhibit these correlated dynamics. And we can even begin to explore scaling laws that go away from master equations for super radiant phenomena, and away also from purely linear regime, to some intermediate crossovers that are dictated by the retardations that happen when one photon goes from one qubit to another qubit. So this was a very fast description of the things we are doing now. We're trying to push the limits of quantum science at macroscopic scales, working both in the vision of connected quantum devices, but also opening new possibilities to explore physical models that did not exist before. because these networks that we have here with retarded interactions only exist because now we can build quantum technologies that support them. And just let me close by describing where I work. Oh, sorry, this is not the place. This is the place where I work. You will recognize the building from the famous TV series. We are in this very nice campus of the SIC, the small building here, Institute of Fundamental Physics, with a young and vibrant team of quantum opticians, expressing algorithms, and people that enjoy doing a lot of quantum science and quantum technologies. And we are just one group out of very big network. Spain has now more groups doing quantum technologies. You can find many of them in this webpage that we created together with Quantum Spain and TalentQ and the Spanish Network of Quantum Information and Quantum Technologies. And part of this network is what we call the Quantum Technologies Platform in the SIC, with 21 research centers and 35 research groups working on quantum computing, quantum communication, quantum sensing, and fabrication of quantum technologies. And I close this here, and thank you for your patience.
Awesome. Thank you very much, Juan Jose. This was really wonderful talk, and I'm sure there are questions. So I put the time for discussion. And please, if you have any question, raise your hand, and we will unmute you. Come on, I'm sure there are many questions. Hector, we have one. Okay, I think you're unmuted already or not. Alberto, can you check if Hector is unmuted?
I am muted.
Oh yeah, Hector, you can speak.
I can speak, I think.
Okay.
Can you hear me?
Yeah, we can hear you.
Wonderful talk. Thank you very much. Yes, I'm curious about the very beginning part of your talk when you talk about this G protocol to retrieve the information from one qubit to another. And also you mentioned during the talk non-Markovian system and so on. So I'm wondering if you can also can derive some protocol doable in experiment for those scenarios in which you have a non-Markovian situation and so on. And also the derivation that you already showed there has to do with some limit of more classical light, or also is valid in the very quantum few photon regime. So that's two questions. I'm just curious.
Okay, so there are many questions in that question. There are many reasons why this system is not Markovian. One reason why it's not Markovian is that the photons that are emitted eventually bounce back. Okay, so that means that the waveguide has memory, and actually has infinite memory, because you can store many photons as you want. So that's one limitation that makes the problem quite rich already in a simple scenario. There is another non-Markovian limit, is that we are shaping photons by transforming in time the light-matter interaction, something we can do with atoms, but is more easily done with circuits. And these controls, they can be as fast as the length of the photons themselves. And this means that some of the approximations we typically do in quantum optics, they may be wrong, or we have to redo them in different ways. So it forces a little bit of development on how more careful derivation of how the light-matter interactions are controlled in these devices. And there are things we have been able to do, but there are limits on what we have been able to achieve. Then you asked about the conversion of information between qubits. I didn't get that completely.
I think you already covered somehow, because I was wondering about this protocol of G in and G out. How you do that in the presence of this complex scenario, open system and non-Markovian in particular. And also, the second question was, one limit is the non-Markovian thing, and the other thing that I'm curious about is if it is valid for few photons scenario. It's something like sounds to me like some sort of classical or semi-classical argument what you wrote here in the corner.
Right. Let me go step by step. So the first part is the transaction of information between the qubit and a propagating photon. And we do this with a single excitation wave function. It's a limit that is valid. It's accepted by the theory, where we either have the qubit in the ground state and no energy is going to be produced, or the qubit is excited and one photon at most can be produced. That's a limit of just one photon, where we can, provided that the photon is never going back, it's not reflected, we do short enough times, we can develop a theory that only involves the left part of the experiment. Then the other thing that we do is we are going to do the same thing here. So we will develop a theory for the incoming photon, which is a time reverse theory of the emission of the photon. So that those two theories are very easy. What we have to achieve is that no photon bounces back. So we need to shape this part so that the photon is fully absorbed. Because if it's not fully absorbed, then we will have a scenario, like I showed here before, where you have a photon bouncing back and forth, and our theory is broken. This is when we reach one reason for non-Markovianity. The second part is when you have more photons, the scheme doesn't work. And then we have to find new theoretical tools. And it aims more towards the second part of the talk, which is the outlook. So we have been able to do, like these delayed interactions, motivated us to have equations where we have more photons and we have more qubits. And this is the way we are doing it. We are developing equations not for the observables, not for the wave functions, but for the observables. And these equations seem to be more accessible. They can be more manipulated, and in principle, they are more generic, and they can reproduce experiments like I showed before here, where you can have 1, 2, 3, 4, 5, 6, 8 atoms, and each of them can generate up to one photon, and we can simulate them all, and we can extract physical conclusions from them. And so that theory seems to be, there are some uncontrolled approximations, but they seem to be working very well. And this is our path towards the future, to have this kind of many-body physics with more photons and more emitters with more sophisticated mathematical tools.
Okay. Okay, thank you.
Very good. Pepa, you are next. Let's see if... Yeah.
Okay.
Okay.
Can you hear me?
Yeah, we can barely hear you. Please
Okay.
approach.
Thank you very much for the nice talk. I have a very general question, and it's more a curiosity. And I'm wondering if is there research towards the development of high frequency qubits? I mean, qubits having larger energy difference between levels, so they can operate at larger temperatures. So you will not need a large number of dilution refrigerators connected together, which is also very impractical.
Yeah. Well, I mean, my feeling is that this field of research has been always constrained to low energy microwaves because it's very cheap. It's something you can do with FPGAs and tools that are already available from the industry of telecommunications, basically cell phones and this kind of thing. So it has been accessible and it has grown very fast because it can be done very cheaply, or comparatively cheaply at least. We could push towards higher energy qubits. There are different ways to do that. One would be to, for instance, you can go to high temperature superconductors, or you can go towards circuits that have higher resonances or different kind of Josephson junctions and circuits that support it. The problem there is the control electronics. Then you need higher energy microwave electronics, which is more expensive. I think it's dominated by the wall of radar technologies and military technologies, but it can be done. We have people in Spain like Pablo Acedo who have worked on this kind of electronics. So in principle, it should be feasible, but it may be more expensive, of course. I don't know if this would be associated to improvements in the coherence. Depends on the source of the coherence. You can have dephasing, which is not necessarily associated to the energy difference between the levels of the qubit. So that could be something to be investigated. But yeah, it's I think right now the limitation has been money, to be honest. But I'm not experimentalist, so maybe it's a biased view.
Okay, thank you.
Thank you. We have time for a last question. Hector, is this the same hand or is this the second hand? I don't know. Well, I have one question, a curiosity. So I would like to know, this is a general question, how much agnostic is this to what's the technology you have at the nodes? So suppose you're working with photonics computing already.
Yeah.
So would this scheme be, would you have to go through the cavity, the atom of the cavity again and produce this flying qubit like that, or you could bypass
To be honest, in principle, the cavity is not required.
that?
The cavity is something that is convenient for some superconducting experiments because if you have a cavity and you move your qubit away from the resonance of the cavity, it's a way to protect it.
Mm.
For example, for superconducting circuits, it's not essential, and the experiment that I showed before from Andrew Killian had no cavity.
Mm.
The original proposal by Thira, Mabuchi, Kimball, and Solar had a cavity because they use the cavity both to have a qubit stored, but also as a mechanism to collect and guide the photon. And that sense, the cavity was is a useful tool when you have photons in the optical regime as a way to collect objects that happen in a 3D scenario. So you need to collect all the light from the atom, and that's very useful. The more important ingredient, I think, is that you need to have a strong light matter coupling. And so you need to be able to faithfully convert the excitation of the atom into a single propagating photon in a single mode.
Yeah.
And that has been a challenge for AMO technologies for a long time. I think they are catching up. There may be experiments, as I said, with ions, or maybe with epicenters, or with other objects that have these light matter interactions. And then another thing that could happen in the near future is that instead of having these links where the microwave tube sits in between fridges, you can also use a technology called transduction, which is you can convert photons from microwave regime into photons in the optical regime. And this is indeed what Johannes Fink was doing in this project, and they succeeded in achieving a strong microwave photon coupling, microwave optical coupling in these devices, and there are many groups researching on that direction. So there are more platforms that can be incorporated. This paradigm is very generic to quantum optical systems with light matter interactions. And there may be even ideas that we have not discussed that are also being studied in the lab.
So, but then you agree this would be a challenge for just pure photonic computers?
Not necessarily. You could have a superconducting platform that works very well, and then you have an optical connection, or you can have a fully optical system like MB centers, which talk to each other through different devices. Or
No, I'm not talking about just purely photonic integrated. Integrated.
Yeah, well,
I mean, just pure photons. If you don't have matter in between.
Pure photons, they are always moving. So
yeah, this is why maybe it's an advantage on one side. On the other hand, how do you get one out of that and you control it exactly the way? I mean,
yeah, the other possibility is you go towards psi-quantum approach, where they're always generating photons and consuming them instantaneously. And those photons can come from different stations and they can be combined in the same experiment. I was thinking more on the fact that we have some kind of long-lived qubits where you can store the photon in a single place and keep it there. And that is useful already for things like quantum repeaters, but also for memories and also for processing, because it could be faster than other experiments with measurements. So yeah, it's a paradigm of having stationary qubits and moving qubits talking to each other.
Very good. So I don't see more questions. It's been, I think it's the time is over. It has been extremely interesting, and I want to thank Juan José again for his time and his knowledge, for sharing his insights. And I want to thank you all for attending the seminar, and I hope you reconvene in 2 weeks again with another interesting seminar. Thanks to everybody. Thanks to Juanjo, and see you again. Keep in touch. Goodbye.
Thank you. Goodbye. Thank you.